Okay, so we've talked about emulsion polymerization. Now I want to extend this to what mini emulsions are generically. So we're going to miniaturize the system, and there's a few concepts that are really important in nanotechnology, and one of them is asphalt ripening, and that will come into play in this part. So we've seen this over the last 3 lectures, how emulsion polymerization works. We talked about the rates, we talked about the mechanism, and we talked about lots of events that have happened. And hopefully we have a relatively clear understanding now on how this process works and how we can use this as a tool to make small spherical particles of, or small particles of polymer material. And obviously if you change the monomers, you can get lots of different types of particles out of that. So now one of the questions is, okay, so I have monomer droplets in an emulsion polymerization, and we've seen before that these didn't really play an important role apart from acting like a reservoir for monomer to be transported through the water phase into the particles. So now one of the questions you could ask yourself, what happens now if I would shrink my monomer droplets? So now typically, they're about 10 microns, a couple of microns in the order scale. What if I make them smaller? Yeah. What if I have a way in order to make these things way smaller? So and as a result of that, I've taken a table from a review by Shork. And it illustrates it really nicely. So it has a base parameters of temperature is fixed, monomer to water ratio is given, the surfactant CMC is known, the concentration of the surfactant is given, surfactant surface area is known, the number of molecules per micelle is known, and the monomer water saturation concentration is known. And as a result of that, we can calculate all these type of things that are displayed in this graph here. So in a typical emulsion polymerization, if I just chuck in my monomer and stir it, my monomer droplet diameter is around, say, 10 microns. Yeah, and knowing all these things at the bottom, you could calculate it for yourself. Yeah, we have calculated how many micelles, if you know when they group together and how big they are, so you can calculate how many you've got. And you see here, for example, that, the volume of monomer droplets is given there, the total number of monomer droplets, the total area of the droplets, we've done that before. And in this particular case, you have like 247 square meters per liter, the total surface area of the micelles. And you see here that the total surface area of the micelles in this particular case is 5,246, so way larger. So you would get entry into a micelle, and therefore you end up with the small particles in this particular case. Also because the number of these micelles is very large. So you get exclusive entry into the micelle, so the number of particles you get is roughly the same as the numbers of micelles you've got. Yeah? The total surface area of the droplets in this particular case is only 4.5%. So occasionally you might get entry into a droplet, but in most cases you don't. So now hypothetically what we've done is like, what if we just lower the droplet diameter? So, put a more hardcore stirrer in it, for example. So let's shrink it with a factor of 10. And you suddenly see that the total area of droplets and the surface area of the micelle starts to be competitive with each other. So you get about 45% of the total surface area is now the area of the droplets. So droplets start to compete with the micelles, which means our picture of emulsion polymerization no longer is as simple as we think. We have to now take into account that droplets can also nucleate. And what if I make my monomer droplets diameter even smaller, so to 0.5 micron, 500 nanometer? In that particular case, 90% of my surface area is as a result of my monomer droplets. And I no longer have that many micelles left. And what if I can make it even smaller? What if I can make monomer droplets of 100 nanometer? If I have droplets of 100 nanometer, I have no more micelles left. Why not? Because I need my surfactant molecules to stabilize the very large surface area of my monomer droplets. So effectively, I've got no micelles and only monomer droplets. And now only monomer droplets play a role in the reaction. That's quite an interesting system, because if I would have monomer droplets only and the water phase no longer then is important, I can do reactions exclusively in really small droplets, and I would simplify my system a lot. So if I'm able to shrink my droplets small enough, as in sub-micron, or even a factor of 10 smaller, like, around 100 nanometer, then I no longer have to worry about transport through the water phase. Because once I enter a monomer droplet, that's where everything is going to happen, and all my monomer is there in the first place. And that would mean I can put a lot of little things in there. So in a way, what you do is you shrink, in a way, a suspension type of reaction, yeah? Your monomer droplet is your reactor, and now you just have a mini reactor. So this concept was pioneered by Ugelstad, El-Azer, and Van der Hoef in 1973 for the first time when it comes down to polymerization reactions. Obviously, small droplets, they were known a little bit before, but that area was up and coming. So effectively what you've got is you have tiny little droplets that are stabilized by surfactants, and each little droplet is your mini reactor, and you can do any chemistry in there what you like. Yeah, and in this particular case, these guys did a polymer reaction. So I've put some references at the bottom here. So the original paper by Ugelstad, El-Azer, and Van der Hoef from 1973, and then two reviews, which we've taken some images in this presentation from Shork, and one by Jose Asua, and some really nice review of making what kind of stuff you can make, because obviously you can put all kinds of chemicals or other objects inside these droplets, so you can make composites and hybrids, by Katharina Landvester in Angewandte Chemie relatively recently. Okay, so this looks simple, right? I just shrink my system, and if I can do this, fantastic, I can do polycondensation reactions, I can do organic chemistry, I can do anything I like, because this now is my round bottom flask. Each droplet is my round bottom flask. It's an enclosed system. The water phase is just a solvent, and I end up with nanoscopic objects. Great. So the question is, first of all, how do I make small droplets? Because if I just use a blender, then I won't really drop below a micron. And the answer is more power. So in a lab, typically you use an ultrasonic tip, and what you get, you first make a coarse emulsion, and then in a way you just nuke it with ultrasound. Ultrasound causes cavitation, which means it's high energy, and it breaks up droplets into smaller droplets. And as a result of that, you can homogenize, it's called homogenization, the system into droplets that are way below a micron. So this is one way of doing it. These tips are very high power. You don't want to have your finger in the jar when you switch it on, because it will just disintegrate your finger. Yeah? So it's high power. So another way of doing it is to use one of these devices. And basically what it is it's quite a simple thing. So you go with a coarse dispersion into a cylindrical type of object, and then it hits a wall. And there's two very, very narrow orifices, or in a way a cylindrical orifice in this case, that basically pushes the system out of it. And because the gaps are really narrow, you get all kinds of instabilities in droplets, because they get elongated. And as a result of that, they break up. Again, this is also very high power, because the pressure drop across the system from the center to the left is massive. Yeah? And if you recycle this a few times, you can go from a coarse emulsion to a mini emulsion. Obviously, you loop it around a few times, and then you'll end up with a nice dispersion of very small droplets in water. And then you think, right, fantastic, I've got that sorted, so I can do whatever I want to do, and all chemistry would work. And this is what people initially thought. And then there was a problem. And this is the problem. When you make stuff small, this effect, which is referred to as Asphalt ripening, becomes a massive problem. And Asphalt ripening is directly linked to a Laplace pressure of a droplet. A small droplet, remember, 2 times interfacial tension over the radius, has got a high Laplace pressure. A large droplet has a low Laplace pressure. High pressure is higher solubility. It's kind of bad. And here you see Asphalt ripening of gas bubbles in this particular case. So the dark objects are bubbles, and the pictures are taken as a function of time, A, B, C, D. This is a Nature Materials paper from a few years back. And what you can see is that the large bubbles get larger and the small bubbles disappear slowly but surely. And how can you think about this? Well, imagine that you are a molecule in this gas bubble, or you're a molecule in a droplet. It's similar, yeah? And you're on the interface. You don't want to be on the interface because you'll have some tension with the continuous phase, yeah? If you're a small droplet or bubble, the likelihood that you're on the interface is pretty high, yeah? And you only have a few friends that are in the middle. If you're a large droplet, then the number of molecules that are on the interface with respect to the ones that are on the bulk is way less. So the fraction that has a tension is way less. So as a result of that, that system is a bit more stable. So that is how you could, like, well, in a way, qualitatively could think about Asphalt ripening. But the thing to remember is, Asphalt ripening is important. What happens? Larger bubbles or larger droplets become larger, and small ones disappear. That's why, you know, it's referred to as ripening. So, how important is this? Is given here for a range of materials. So I've just put them all in a kitchen blender, and I just want to see, because obviously not all my droplets are exactly the same size, and I'm just going to see, you know, how stable is this? So if I put an organic solvent and I make this mini emulsion of droplets of 100 nanometer, how long does it stay a mini emulsion? Because obviously if I want to do chemistry in there, then I have to have a certain stability, because if my droplets, you know, are not the same anymore, then I can't do that reaction. So, and people that looked at that developed this theory over here, and the theory basically says that, well, 2 things. One is the diameter. The top equation is the diameter of the droplet as a function of time is the cubic root of the growth rate due to Asphalt ripening of this droplet plus the original diameter to the power 3. Yeah? So that kind of makes sense. And then this growth rate was determined, and was the equation below there. So it's 8 times the fusion coefficient of this molecule through the water phase times the concentration, the saturation concentration of the molecule in the water, times the molar volume of this molecule, times the interfacial tension in this case, divided by 9 times RT, R being the gas constant and T being the temperature. And people have measured this for a large range of materials, so I've put a graph in there from a paper. I've referred to the paper at the bottom there. And then for a range of monomers in this case, so they've done methyl methacrylate, butyl acrylate, styrene, and the most hydrophobic one being lauryl methacrylate, putting all these equations in there and calculated the rate of Asphalt ripening. Now, we've put these things nicely in these 2 equations, so let's go to the next slide and see what it means to make that clear. So these are those equations used. And what you can clearly see, if I start off with a droplet diameter of 100 nanometer, And if it would be methyl methacrylate, you know, within an hour, my droplet is over a micron. So that means it ripens pretty fast, which means my mini emulsion is not really long a mini emulsion. Now, if I go to styrene, now styrene already, remember, is like a water solubility of like 3.5 millimoles per liter. So it's not that water soluble. But again, you know, it ripens pretty quick. From 100 nanometer, you know, 50 minutes later, you're at 500 nanometer. So again, you no longer have this very, very nano confinement. So only lauryl methacrylate seems to, which has a very, very long aliphatic chain, seems to remain stable over a prolonged period of time. So this would mean that if this would be the case, this would severely limit my application of mini emulsions, right? Because I can only do it for very hydrophobic components if water is my medium, my dispersion medium, which means that my brilliant idea of making mini emulsions of everything then would completely fall apart, and it will be a technique that can only be used for a very restricted amount of materials. Now, here you see the same reason. You use the same equation, and it tells you this, the MTA equation, which we've seen in the last lecture. And, well, basically, if you would modify it and say, okay, if there's no polymer in there at all, so all those terms disappear, and the only thing that's left, basically, is the interfacial tension part, in order to calculate the difference in energy or in chemical potential. Then you can see that the chemical potential, in a way, goes up for small systems, because basically it's 2 times the interfacial tension divided by the radius. And you want to minimize the energy, not maximize the energy, which means that small droplets will disappear because you know, energy goes up there, and basically they ripen towards the larger ones. So the larger ones are more stable than the small ones. So Asphalt ripening, always small droplets disappear in favor of larger ones. Not by colliding into each other. It's not that a small droplet bumps into a large one. That's different. It's through the fusion, right? The small one goes diffusion through the continuous phase, and that's how the system ripens. Okay, so in lectures 2 to 4, we saw that the particles could swell, say, 3 to 4 times the volume. Yeah? And this large equation at the top, we had this J in there, which was the number degree of polymerization. And we basically set that to infinity, because that was very large. Yeah? So if we would do that, then the volumetric swelling ratio, which you can calculate if you would plot those equations, so I've replotted the graph on the left there, it will be roughly 4.5. So 4 to 5 times you could swell. Yeah? What happens now if I make this polymer way shorter? So I don't have high molecular weight polymer, but low molecular weight system. So what now if J is 5 or J is 2, so a dimer of styrene or a pentamer of styrene, or just another molecule that's small that roughly takes up in space 5 times the volume of styrene? You'll see that the volumetric swelling ratio shoots up, which means that material would love to attract more monomer, which effectively means that if I would have a little bit of low molecular weight, very hydrophobic material, I can retard asphalt ripening. So before I thought that, okay, I have droplets of MMA or droplets of styrene, and it's game over because after 50 minutes, you know, it's completely ripened. But if I now put in, say, you know, 4 to 8 weight% of something that's hydrophobic, I can massively retard asphalt ripening. So I might still be able to make stable systems. That's what this kind of story is saying. So how does that work? So in practice, if we disperse oil droplets in water, we have to use a hydrophobic compound, a compound that is so hydrophobic that its water solubility is tiny. That hydrophobic compound will restrict the rate of asphalt ripening for the other molecules that are in there. So, for example, hexadecane, C16 is a good one, or long-chain methacrylates in this case, such as stearyl methacrylate. If you add 4 to 8 weight % to your formulation, then you can end up with a stable mini-emulsion, with stable meaning instead of ripening in 50 minutes, it'll be stable for half a year to a year, or even longer. That basically means that then you can start doing, real interesting chemistry. So the key is that this hydrophobe in this case, which we refer to as co-stabilizer because it stabilizes the droplets against ripening, is not, or hardly, and hardly being like nanomolar per liter or something, soluble in the continuous phase. So you can think of this the other way around. You can think of this, okay, what about an inverse mini-emulsion? So I have tiny water droplets dispersed in oil. Yeah? What compounds would I use then? I have to use something that's not soluble in the continuous phase. Salt is not very soluble in oil, so that would be a good thing. Yeah? So I can use salts for this particular system. So okay, so here's a nice inorganic experiment. And I took the actual experiment from Katharina Landsvester's website years ago, and now I can't find it back. So I put it into brackets. This wasn't my idea. It's Katharina's idea. I think we still should do it in the lab just to check. So I'll see whether we can do it, and I'll show you. I'll upload the video later because it's quite fun. So so this is year 1 inorganic chemistry. Yeah, iron 3+, 4 units of that. Plus in a salt form, so for example, you could just use the iron chloride for that. And then you have iron 2 with 6 cyano groups there. Yeah, and if you mix these two things, you get 2 different oxidation states of iron, which causes an extremely intense color, which is known as Prussian blue. Yeah, so if I mix salt A with salt B, in this case, it reacts almost instantaneously, and I get very, very dark blue material. Yeah? I don't know whether you've done that in year 1, but now we're going to do this slightly different. So I'm going to make 2 inverse mini-emulsions. So water droplets dispersed in oil, so I use a surfactant that stabilizes this, and then in one of my water phases I have this Fe3Cl3 as a salt, and the other one in a different jar, I've got K4, the potassium salt of this iron cyanide. Yeah? And then I make a mini emulsion of one and a mini emulsion of the other one, and then I mix them, pour them together, basically. So the question now is, what happens if I pour these together? A, nothing, or B, the reaction gets on the way. So one mini emulsion system of one salt, the other one of the other salt, so tiny water droplets containing one salt, mix the two, as in pouring them together. What happens? A, nothing. B, Prussian blue gets formed. 50-50, exactly. Whoa. Although people keep changing their mind, but nobody dares to swap over to one or the other. Yeah, click, 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 click. Yeah? Okay, think about it. Asphalt ripening gets suppressed. Yeah? The salt does not dissolve in the continuous phase. The salt does not dissolve in the oil. Yeah? So I have one water droplet with one salt in there, another water droplet with the other in there, and they don't see each other. It's a compartmentalized system. Yeah? Reactant A is in one, reactant B is in the other one. The only way how reactant A and reactant B could react is if A diffuses through the continuous phase into B, or B into A, or if the two droplets would merge. Yeah? If the droplets are colloidally stable, if I use the right surfactant, they wouldn't bump into each other. It's a colloidally stable system. My mini emulsion stays stable, so basically nothing happens. So I have reactant A and reactant B in one reaction flask, but nothing will happen because the system is compartmentalized. I have a picture of this on the next slide, I think. So here you see the end result. This is the picture I took from Katarina's website. So here on you see a bunch of vials here. So on the left you see this iron chloride, and slightly browny, yellowy, and then this iron cyanide complex there, dispersed in oil. Why does it look a little bit milky? Any idea? So why does this vial look a bit milky? Why is it not completely transparent? Who's got a view on that? So water droplets dispersed in oil. Why is the vial not transparent? Yeah, scattering. So because, yeah, it's exactly, it's scattering. Because the refractive indices of these two materials are different, and as a result of that, you get scattering. So milk is literally the other way around. Oil droplets in water. It's white because it scatters. Yeah. This one is water droplets with a bit of the salt in it, dispersed in oil, scatters, and that's why it looks a little bit milky. Yeah. So then I pour these two things together. There you go. Nothing happens. Yeah, obviously it looks a little bit the same, a bit lighter than the iron chloride one because you mix the two, but nothing happens. So the only way how I can make this reaction work, if I would have to redistribute the content of these individual droplets. So basically, if I would nuke it with my ultrasound tip, I will break droplets apart and scramble everything. Then this reaction would take place. And that's exactly what they did. So they have this system, and they use ultrasound. Bam, there you go. Yeah? So this is quite interesting. You can prevent the reaction from happening because reactant A is in a different compartment than in reactant B, but they're still in the same system. And then when you want it to happen, you make sure that these droplets fuse with each other, and then you get reaction. So it's quite an interesting concept. Okay, so in a way, mini emulsion polymerization, rather than just mini emulsion, is exactly the same as emulsion polymerization. Everything what happens in emulsion polymerization happens in mini emulsion polymerization as well. But on top of that, you have to look after this monomer droplet. The monomer droplet starts to play a really important role. So basically it means that when you get the initiation, you have your Zemer. Normally it could enter a micelle, or it could further propagate, or it could enter an existing particle. Now it can enter a monomer droplet. And then the monomer droplet suddenly becomes a particle. Yeah? So that needs to be taken into account. So the same kinetics are applicable. However, now you have to take into account that the monomer droplets are small, so entry in the monomer droplet starts to become very important, if not the most important system. So here you see just a nice example of a system that worked. So they used hexadecane as co-stabilizer, say 4 to 5 weight % or something, SD as a surfactant, and for some bizarre reason they get really narrow particle size distributions in this case. Normally it's a little bit more a random mess, but if you're lucky, they got lucky, all the particles are roughly the same size. And obviously, the more soap you use, the smaller your particles become, yeah, on average. Because obviously, the soap molecules can stabilize interface. If you add more soap, you can generate more interface. Therefore, you can make small droplets. So typically here you can see, you can go down to 42 nanometer in diameter quite easily. So you can make really, really small particles if you want to with this technology. Okay. So key advantages of a mini emulsion is that you do not rely, you basically cancel out the transport through the water phase. So each droplet is its own individual reactor. And then your mind can just go crazy because you can put, imagine your droplet is just your round bottom flask. You can just put anything in your round bottom flask, and therefore you can put anything in the droplet, providing that you can stabilize this droplet, and obviously logically that the object you put in is not way larger than the droplet. Yeah, so if you have a 100 nanometer droplet, you don't want to put a piece of clay in there that's a micron big, because it won't fit. Yeah. So, and if you've got that, you can do all kinds of stuff. So you can, you can make artificial lattices, which is, for example, really important in healthcare. They use this polylactic acid, yeah, and they have to make small particles out of this. So what do? They dissolve it in an organic solvent. They basically homogenize it with either with ultrasound or with a high pressure homogenizer, and then they blow off the low boiling organic solvent, and then you have polylactic acid particles. And typically they put a drug in there as well, so you have a bit of a mixture of these two, a composite of these two. Yeah, and those things are used in healthcare. You can encapsulate liquids if you want to. So you can encapsulate all kinds of oils. Maybe you want to do that for heat change exchange materials. So you can imagine, like, if I would have an oil in there that melts at 25 degrees Celsius, then I could use this as a cooling refrigerant, because basically my latent heat of melting would store energy, store and release energy. So you can basically keep the temperatures of buildings a bit more constant. You can play with particle sizes, because I can make one mini emulsion with large particles and one with small particles, and I can blend them together. So I can make really high solid systems, which normally is not possible. If all my latex particles are the same size, or all my droplets are the same size, I can go to 64 volume% and then I jam, and I have a solid. But if they're all over the place, you can think of systems, bimodal, trimodal distributions, or even if you think really extreme, you can fractalize it. So you can fill up the interstitial spaces and again and again and again. So in theory, you could go all the way up to, say, 100% solids. Yeah? And people have gone up to 90, 95%. Dispersed phase. So that's pretty cool. Because it's their own reactor, you can all do kind of living systems. You can do organic chemistry in there. You can do anything you like, basically. And the cool thing is that you can do reactions relatively fast. You have good heat transfer. You have very low viscous systems, so control is really good. You have an extremely large surface area, so interfacial reactions would work really well too. Sometimes people that want to react to organic chemistry, they want to react one component that's quite hydrophilic and the other half is very hydrophobic, and they don't really know how to mix these two. Yeah, you can just make a mini emulsion of one, and the other one is in the continuous phase, and the surface area is massive, so the concentration locally is very high, so you get a very fast reaction. The only downside is you have to get rid of the surfactant, but that's only 1 or 2 weight%, and typically in organic chemistry you have all kinds of side reactions, so in order to get rid of that, it's not that difficult. Not many people do that though, so it's quite interesting that not many people in organic chemistry use this technology. So it's used a lot in the food industry, a lot in people that look into energy and in diagnostics, in healthcare, and is used a lot as drug delivery. It's not used a lot in organic synthesis though. So, you might want to think about that a little bit. Okay,